Mark asked me about number 6 from the homework last day, which was an exponential equation. You can see we're going to be graphing a whole bunch of exponential equations. And it turns out any equation that has x as an exponent will have a similar shape, the same way every equation with a squared was the parabola in disguise. Maybe stretched, it maybe flipped, it maybe moved around, but it was a parabola. Turns out any equation where the x is an exponent, we're going to do the same thing you guys did last year for the parabola. We're going to memorize some key concepts, some key components. So, an exponential equation is a function of the form f of x, and remember, f of x is the same as y equals a base to the x, where x is an exponent. Oh, and then we're going to say, just like for the parabola, you could put something in front of the x squared. You can have a number in front of the base as well. And you notice we're using an a just like you did for the parabola last year. We're using b for base. Kind of makes sense. Brianna, we have to add some restrictions. A can't be 0, which is why I wrote that, because if a was 0, what's 0 times anything? 0, that's not going to be a graph, funky. That's going to be a normal blood graph. Oh, and I'm going to add one more restriction. The base, b, must be positive. What I'm going to show you will not work for a negative number to an exponent. It won't. And we'll talk about why another time. And the base can't be 1. And the reason is, what's 1 squared?
1.
What's 1 cubed?
1.
What's 1 to the 4th? 1. What's 1 to the... 1 does not behave like any of the other exponential bases, because you keep getting the same answer. So I'm being fussy, Julia, but I always point it. I'm glad that the textbook points that out. If I had been creating these notes, I would have pointed it out the same as saying, okay, what we're really saying is an exponential graph has a positive, non-zero, non-1 number as its base. Oh, and it can't have a 0 in front because multiplying anything by 0 makes it all cancel. Let's compare 2. We're going to compare 2 to the x and 1/2 to the x. By the way, how are 2 and 1/2 related? One's a reciprocal of the other. Okay, we'll talk about that. First thing we're going to do is we're going to open up our graphing software, if you haven't already. Just a reminder, on my menu, my menus are in different locations. So my graph is option 5. What's your graph? Option what?
3.
Okay, so go to option 3. I'm going to go to option 5. And once you're here, I want, before I even start to graph anything, I want to make my graph paper look like their graph paper in the textbook. How far left does this piece of graph paper go? Count the number of squares. Is it 10? Okay, so it goes -10, +10, -10, +10. We said that you could change the view window. Now, how do we do that? What is view window? It's yellow, and it's above F3. So you hit the, I got you, hang on. You're going to hit the yellow button and go view window. And you may or may not already be X-min, -10, X-max 10. And there is a shortcut. It turns out your graphing calculator has this stored. If you hit F3 standard, it brings that up. Now I'll pause. Yes?
Actually...
-10 and 10 is going to be close enough.
Oh, I was going to say it's 11.
I know. That's going to be close enough.
Okay.
Is there anybody that can't get here? Tell me now. Okay? So, are you able to get to this screen?
Yes.
So, to get to view window, see where my arrow is moving? Brandon, look up. View window is in yellow. Look up. Leave him alone, Jordan. View window is in yellow above F3. So anything yellow means shift. And when you do that, the only option is view window. You can zoom into any area that you want to, but it turns out if you press standard, which is STD, not what you think it stands for, F3, it'll automatically fill in an X-min of -10, an X-max of 10, a Y-min of -10, a Y-max of 10. That's fancy lingo for saying we're going to go -10 down, -10 up, -10 left, -10 right. Also, a reminder, scale is what you want. Can you stop dropping the pen, Jacob? Thanks, guys. I'm dealing with lots of extraneous noise. I don't need it right now. Scale is what you want each hash mark to be. If I wanted to, just look up to show you what it looks like. I could go up with a scale of 2, and if I show you that screen, oh, it won't let me do anything. I'll just graph something. If I show you that screen, you can see it goes up 2, 4, 6, 8, 10. You can change the scale to whatever you want, but I'm going to go View Window Standard. Okay, then how do we exit from this menu? That's a hint. How do we exit from this menu? Exit. So Rachel, if you get stuck somewhere, when in doubt, 2 things. Try hitting exit, and if that doesn't work, try going Shift Exit, because what's in yellow above the word exit? Quit. That'll bail you out of about 90% of stuff. So exit. Okay? Really obscure things. If you have a graph here, you want to delete it, which is F2. If yours is clear already, great. But clear any graphs that are there. If you have a graph there, clear it. F2. I know, hang on. Okay. Now, you also want to make sure that you have the right type of graph. You were away when I did the graphing calculator lesson. Okay. So, listen, look up. Okay, pick up whatever you're going to pick up, and then we need to have an attention span here longer than 5 seconds, people. Okay? Let's say again, listen close. You want to have the right type of graph. What do you think you're going to hit? Which is F3, right? Now, there's a whole bunch of different ways to graph. We want y equals. And Rachel, that was also where you were getting weird. If you have weird stuff on your screen, probably instead of hitting View Window, which is Shift F3, which you hit fairly often, you accidentally forgot to hit the Shift, and you hit F3 and change the type. Don't freak out. Exit, type, and we go back to y equals. And if you do that, all of our screens should kind of, I think your screens look a tiny bit different, but pretty much like this, yes? Let's type in the first equation. The first equation is this one here, 2 to the x. So you're all going to type 2 to the power of, what's my to the power of button on these things?
The up arrow.
Which is right next to the x squared, right there. The little carré, I think it's called. And then, this is important, all of you, look up. Don't use F5 for x. That's going to give you something wonky. Instead, your x button is right here below the red alpha. That's your x button. How do you store an equation? Hit execute or enter. How do you know it's stored? You'll notice your equal sign got colored in. That's Y1. Okay? What's this look like? How do I draw it? F6, draw. This is an exponential graph. Now, if yours didn't give you that, now is the time to raise your hand and ask, because you absolutely need to know. So, first of all, it says, state the values for A and B for this. Well, what's the base for this equation here? What's B? What's the base? What's the x sitting above? Yeah, keep it obvious. The base is 2. What's the base for the second equation? Y equals 1/2 to the x. 1/2. Is that okay so far? Nothing too radical there. It also says, what's A? Now, this is kind of a question that's so easy that it's tough. A is the number sitting right there. A is the number sitting right there. What number is sitting in front there? It's invisible. We're starting off with A equals 1, and then later on we'll actually put numbers there and see how that affects the graph. Just like you started off with the parabola, y equals 1x squared, although you never bothered writing the 1, and then later on you learned the whole stretch and flip and all that stuff, right? So, in both of these, okay. B says, complete the table of values below. and then sketch it on the grid. Now, I'm going to stay away from the negatives for a second. What we're doing is this. Y equals 2 to the x. We're going to plug in values for x. Let's start, how about right here? Put a 1 there. What's 2 to the 1? In other words, 1 over 2 up is going to be a point on this graph. What's 2 to the 2? 4? You see how we're doing? We're just literally plugging in numbers one at a time, and I'm starting with 1, 2, 3, 4, because that's about the easiest numbers to do math with. You okay with this, Mackenzie? Yeah? So it's going to go through 2 over 1, 2, 3, 4 up. What's 2 to the 3? Don't say 6. Remember, this is 2 times 2 times 2. 8. So it goes through 3, 2, 4, 6, 8. What's 2 to the 4th? 2 times 2 times 2 times 2. And many of you have spotted the pattern of doubling, which is why we almost always start introducing the exponential function with a 2 as a base. What'd you say? 16. Can I fit 16 on my graph? Okay, so I'm not going to bother graphing it. Let's go this way. What's 2 to the 0? What's anything to the 0? You know what? Every exponential graph will have a y-intercept of 0, 1. Because what if instead of graphing 2 to the x power, what if I was graphing 1,000,000 to the x power? What's 1,000,000 to the 0? Still 1. What if I was graphing 1,000,000,000 to the x power? What's 1,000,000,000 to the 0? Still 1. So one of the patterns, so for the parabola, you learned the vertex was a key point. For the exponential graph, one of my key points is going to be the y-intercept, which is actually a really nice point. 0, 1, the only thing nicer would be 0, 0. I bet I can't get much better than that. What about to the negative 1? Okay. What's 2 to the negative 1? Well, if you had a good teacher, he might have told you that a negative exponent acts like an. So 2 to the negative 1 is really the same as what? So if I go negative 1, I should be about a half high. I'm kind of eyeballing it about there. What about 2 to the negative 2? Well, a negative exponent acts like an elevator. This is 1 over 2 to the 2. Although, what is 2 to the 2? You know what? 1/4. I'm going to eyeball it, Jordan. I'm closer to, it's about there. If those of you in the back kind of eyeball, definitely you can get the negative 2 part correct. Sorry, negative 2 for you guys that way. Negative 2 part correct, eyeball about 1/4 high. What would the next point be? 1/8? Mackenzie, what's your question? Really? Conveniently, there's a spot right here. I'm just saying you could if you really wanted to. 1/8. You know what? Here's what I notice. What if I went like negative 10? This would be 2 to the negative 10 or 1 over 2 to the 10th. What if I went negative 50? It would be 2 to the negative 50 or 1 over 2 to the 50. Will it ever get to 0? You're going to get a smaller and smaller fraction because the bottom of the fraction is going to be 1 over a bigger and bigger and bigger and bigger number. But Mac, it'll never quite get to 0. We say the graph is going to get closer and closer and closer to 0 to the left, and to the right, it's going to shoot off to infinity. Grayson, that's my by hand sketch, but I think you'll agree that looks an awful lot like what the calculator gave us too. Okay? We'll do part D for a second. We can fill in some of this already. You guys have the graph in front of you. What's the domain? How far left does this graph go? I know, sorry. How far left does this graph go? By the way, in your face, those of you who can't see and aren't willing to move to the front, just saying. How far right does this graph go?
As far as possible.
As a number, please?
All real numbers.
Oh, you know what? What's my domain? All reals, because it goes to negative infinity, positive infinity. Look, see it? That's why I put arrows on either end. Domain is how far left, right? By the way, in a couple of days, you ready? I'm going to give you this graph's inverse. What will the range of this graph's inverse be? All reals. Because we'll switch the x and y around and the domain will become the range. Are you seeing why I said this notion of an inverse, Rachel, was so useful? I can already predict what the inverse graph will look like, and I haven't even told you what it is. What about the range? How high does this graph go? How low? It gets closer and closer and closer and closer and closer and closer and closer to 0. Does it ever touch 0? No. So if it touched 0, don't write this down, we would go like this. But does it touch 0? Well, then we delete the or equal to, just everything above 0. By the way, when I show you the inverse, what do you think the domain of the inverse will be? Everything to the right of 0. Okay. What's the x-intercept? It's a trick question. None. By the way, when I show you the inverse, which intercept won't it have? A y-intercept. It won't cross the y-axis. Again, Brianna, see, we don't even know what the inverse graph is, but because I know that an inverse switches the x and y around, I can make a lot of predictions about what it must look like. What's the y-intercept?
0.
By the way, what will the x-intercept of the inverse be? 1, 0, because the x and y switch around. Telling you, it will. And then here is a new term. We have something in math that we call an asymptote. You may have seen this last year. Probably not. What an asymptote is, it's a line that a graph gets closer and closer and closer and closer and closer and closer and closer to, but never touches. In this graph, it's the height of 0. It gets closer and closer and closer and closer and closer, but never touches. What's the asymptote here? The height of 0. What's the asymptote here? What's the asymptote here?
The height of 0.
I don't want to write that. That's too much writing. Oh, I can write it short. You know what height is on a graph? It gets closer and closer to the line y equals 0, which is a height of 0. Psst. What's the asymptote of the inverse? X equals 0, a vertical line. Or you could say it this way, Mackenzie. This exponential graph has the x-axis as an asymptote. The inverse, someday, will have the y-axis as an asymptote. It'll get closer and closer and closer to the y-axis, never touch. Okay. Let's try y equals 1/2 to the x. Okay, so let's go to our graphing calculator. How do I get back to the graph menu? How would I exit this screen, for example? There you go. Go up. Delete this equation. F2, are you sure? Yes. Now, for 1/2 to the x, how are we going to have to type the 1/2 brackets? Bracket. And you can either go 1 fraction 2, or you could go 1 divided by 2, same thing. Close bracket. To the power of, don't hit F5 for x, use your x variable, which is that one. How do I store the equation? Execute. Or enter, really is what, it's the equivalent of the enter key on your keyboard. And hit draw. And I think you get this. So, Matt, my friend, I'd like you to mirror me, imitate me. Pencil down. Every exponential graph either looks like this, get your hands up, or like this. Now you need to do it moving forwards with a bit more velocity. Like this, or like this. Move your hands forwards with a bit more velocity. Forwards. 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 You're about to hit them. Every exponential graph looks like this or like this. No, okay, you're not getting it. Move. Move. Stand up. This is going to be your cue for the rest of the unit. I'm picking you because I can trust you. Every exponential graph looks like this or like this. Like this or like this. Like this or like this. Okay? Now they can dodge, but that way I've got 3 people paying attention. Okay? Do you see, Hannah, it's the same shape as before, but instead it descends from left to right. Instead of starting out small and getting bigger, it starts out big and gets smaller. But in fact, you know what? I can show you that these are nice little mirror images of each other. If I, as a second graph 2 to the x. Howdy! Let me just pause the video here. In fact, here's what I've learned a long time ago. If my base is a fraction, it's what we call in physics a decay graph. Matt, here's your cue. Left hand up high, right hand coming down. If my base, and the graph's going to get smaller. If my base is a whole number, not a fraction, it's what we call a growth graph. Right hand down, there you go. Okay. Anytime you want to, you can model it moving back, but anytime you've had a long day, if you want to clip them in the head, that's their fault, not yours. Okay? If you want the points, well, I think 1/2. Did I hear a phone go off? Whose phone was that? It was an alarm. If it goes again, keep an eye on them, folks. First of all, hey, folks, what's 1/2 to the 0 power? What's anything to the 0? Don't say 0, it's 1. Oh, what's 1/2 to the 1 power? I think 1/2, right? Anything to the 1 is itself. 1/2 to the 2, now that means 1/2 squared. We can do this in our head. We could fill this in our head, because what's 1 squared? 2 squared. 1/4. What's 1/2 to the 3rd power? 1/8. I got to be fussy. Technically, it's not doubling. Technically, it's dividing by 2 each time, which is not, but I know what you mean. The denominator is doubling, but because it's in the bottom, I got to be fussy. 1/16. Can you continue the pattern going in the opposite? Well, okay, hang on here. 1/2 to the -1. Now, this would put the 1 onto there, the -1, sorry, onto there, and onto there. It's going to be on the bottom. What does a negative exponent act like? So where will that that 2 to the -1 move? 1/2 to the -1 is 2 times 1, but that's not going to make a difference. What about to the -2? It's going to give you 1/2 to the -2. How does a negative exponent act? Why, kind of like an elevator. So that 2 to the -2 on the bottom is going to move to the top. 4. Spot the pattern. What's the next number if I keep moving to the left? 8. So this graph, I'll do it in blue, is going to go through 3, 8, 2, 4, 1, 2, 0, 1, 1, 1/2. Are you seeing? It is exactly symmetrical, like I said. It's kind of a funky graph, but it's got some nice properties. Is that okay, Rach? Thumbs up. In fact, again, Sterling, in physics, we say the blue one is called a decay graph because it's getting smaller. Oh, a fractional base should get smaller. That kind of makes sense because I always think of fractions as small numbers. The black one is a growth graph. It's getting bigger, and that's when you have a number bigger than 1 as your base, a non-fraction as your base. Hey, what's the domain of the blue graph? How far left? You know what? Same domain. What's the range of the blue graph? Same. What's the x-intercept of the blue graph? It's a trick question. Y-intercept, 0, 1, asymptote. So, aside, Matt, from the shape, all exponential graphs have the same domain, same range, same x-intercept, none, same y-intercept, same equation of asymptote. However, if it's a growth graph, then your right hand will be pointing up in the air. Your right hand will be pointing up in the air. Your left hand will be pointing down. Right? Like that. If it's a decay graph, like that. That's for Matt facing forwards. Key idea, though, is the shape. So, it says complete the following statements using the words increasing or decreasing. 2 to the x, as you move to the right, does it increase or decrease? Look at your graph. 2 to the x, the black one, as you move to the right, because we read from left to right, is it increasing or decreasing? Increasing. It's called a growth function in physics. 1/2 to the x, decreasing. So far, so good. Turn the page. And, hey, little note. Notice it turns out they're reflections of each other in the y-axis. In fact, if you graphed 3 to the x and 1/3 to the x, you would also notice they were symmetrical to each other. If you graphed 9 to the x power and 1/9 to the x power, Jordan, you would notice that they were also lovely little reflections of each other. Okay, now let's see what happens when I muck around with the base. But I'm still going to have AB1. I'm not going to put a coefficient in front of anything. So by using a graphing calculator, hey, which we have, sketch the following. So let's go back to this menu, delete any equations that you have. And the first graph, graph I, is 3 to the x. 3 to the power x. Yes, we're on our graphing calculators, Brianna. Got to stay with us. So delete whatever equations you have there, hit enter to store it, and graph it. Does it still match this same shape that Matt has been demonstrating for us? Yeah? Okay. Now, go back to this menu, exit. Let's, on the same grid, graph this second one under Y2, 10 to the x. Now, before you hit draw, which one do you think should get steeper faster? 3 to the x or 10 to the x? 10 to the x. And it turns out it does. This one to the right, this is 3 to the x. Here, this is 10 to the x. It gets way steeper, way quicker. But, same shape. Now I'll pause. Is there anybody that can't get those? Now is the time to ask, and I'll happily come around and fix the glitches. Logan, you got it okay? So, let me pause. How about I unpause? Okay? So, I think we got this. I'm going to be really, really clever. What I'm going to do is go... There. Okay? You guys can make a sketch in your notes, or if you see what we did, you're also okay. But here's what we're going to summarize in part B. When B is bigger than 1, not a fraction, it increases faster. The bigger B is, the faster you increase, the steeper you get. And then here's how I write when B is a fraction, when it's between 0 and 1, because that's what a fraction is, because we did say B it to be positive. It decreases more sharply as b decreases. Wait a minute, Mr. Dueck. I thought you said as b gets bigger, it gets steeper. But if it's a fraction, if this number gets bigger, the overall answer gets smaller, which is why we did say technically it's decreasing when you have a bigger number at the bottom. You get steeper faster. So it says, without using a graphing calculator, make a sketch of 5 to the x. You don't need to, but I'm telling you, 5 to the x would be between 3 to the x and 10 to the x. No, I'm just walking you through it. Okay? Oh, and Darian, 0.2 to the x, which is between 1/3 and 1/10. I'm telling you, it would be somewhere in there. Somewhere. We're going to get more specific, but for now, we're going to use the technology. By the way, other ways that you can find points. Bring up your grids if you have all 4. Bring up this screen. Here is something I did not show you last time. What does F1 say? Press F1. Now, the first thing it's going to ask you is, which graph do you want to trace? Y1, if you go down arrow. Y2, if you go down arrow. By the way, do me a favor, use your fingers on the buttons. That damages them with pencils or things. Use your fingers. The erasers rip the ink off much faster. Down arrow. So let's go with Y1. So cycle until Y1 is in your top left display. You've all hit trace, F1, and then you cycle. Now, if you go left and right, you're literally tracing along your graph. And can you see, Alyssa, it's giving you x and y coordinates? You can even, as a shortcut, just start to type 3. And it'll jump straight to 3, 27. Or you can type 2, and it'll jump straight to 2, 9. Or you can type negative 1.86, and it'll tell you that you're 0.129584920 high right there. So that's a handy way, Grayson, if you've graphed something on your graphing calculator and they want to get you to give them actual points, use the trace button. You can read right from the graph. You got it okay, Brendan? So look up. Can you get to this screen? Yeah. Look up. When I say look up, keep looking up until I say stop. Okay? Trace is F1. Press F1. Look down. Press F1. And you first of all have to tell it which graph you want to trace. So yours says Y1 equal, right? Okay. Then if it's graphing, wait till it's done graphing. So let me know when it's done graphing, all 4. Okay. So you hit trace. And you can pick Y2 or Y3 or Y4. Go back to Y1. And if you go left and right arrow, it's literally tracing a cursor on the graph. Or if you want to speed things up, because these are going to be often yucky decimals. Hey, what is it when x equals 1.8? If you just type 1.8, the screen will say, enter an x value. If you just type 1.8, right? It does. Yours does not? On the black calculators, does this screen come up during the trace menu? You haven't been trying it? Oh yeah. Who's got my older black? Just Brendan? Zach? Does that screen come up? Have you hit the trace button? Okay, hang on. Pause the video. Okay, we're back. We're back. Okay. So, let's generalize. Part E. What's the x-intercept for any graph that looks like this? What's the y-intercept for any graph that looks like this? When you put a 0 in, anything to the 0 power is 1. What's the domain for any exponential function? Boy, that looks terrible. I can write that better. What's the range for any exponential function? What's the equation of the asymptote? It gets closer and closer to a height of 0, but it's much easier, instead of writing the word height, to use the letter y of equals 0. Turns out there's also a very extra special function. I even have a shirt, and I should have worn it today. I'll wear it after spring break. I have an e to the x shirt. E. 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 You with me? E is not a letter. It is in English. But what do I have on my wall over here? A pi. Pi is a number that goes on forever and ever without repeating. Turns out E is a very special number, in many ways actually more important than pi. It goes on forever without repeating. And many of you have wondered at some of this on your calculator. If on your calculator, go menu and go back to the run menu, so you're in your normal calculator-y thingy. Find your X button right here. Move one over and you have a button that says what? Log. Move one over, you have a button that says ln, or often we say ln, because it's just easier to say. In yellow, right above your ln button, what does it say? If you go shift ln to the 1, that would give you e. E to the 1 will give you the value of e. What's e? 2.718281828, and you think it's going to repeat, but actually just after the screen here, it goes all haywire like pi. That's been proven. So it's not a repeating decimal. It does not go 71828182818281828. It doesn't do that. It's just unfortunate that every calculator I've ever seen only displays enough to make it look like it repeats, but it goes on forever. This is base E. Okay, hang on. So why is E so special? Rachel, it turns out, it seems as though life, DNA, life likes E. The same way those of you that are in physics are sort of noticing that the universe seems to like pi. Pi showed up in our period equation for gravitational force. Life seems to like a base of E. If, for example, you were analyzing the spread of Ebola and you have a whole bunch of data, you would find that Ebola ends up being an exponential graph, and the best base to model it turns out to be E. If you're graphing, for example, the spread of IQ scores in a population of 1 million people, turns out the equation will have an E in it. If you're graphing how populations spread due to birth and fertility rates, it turns out, Logan, trust me, the equation will have an E in it somewhere. It just seems as though life and growth likes that number. And there's a reason why that I won't go into, but it's hugely important. In fact, let's look at one application. So, in mathematics, we wrote the number E is represented as an irrational number like pi. It's called Euler's number if you really want to be fussy. It occurs in finance, in sciences, in computer science. Actually, it occurs all over the place. The value of E is irrational, which means, like pi, it cannot be expressed as a fraction. But it turns out you can calculate it. It's 1 plus 1 over 1 plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 4 factorial plus 1 over 5 factorial plus 1 over 6 factorial. If you do that to infinity, you'll get E. How'd they prove that? It's a long, multi-page proof. You can find better and better approximations by adding more and more terms of this. I'm not gonna, because we just found it on our calculator. The value of E to 9 decimal places is 2.7182818281828, but it doesn't repeat. 2.718281828 ... 2.718281828 ... Doesn't repeat. So there's 10,000 digits of E. You could do a search for 1 billion digits of E. You'd probably find it somewhere. So, you ready? We are going to graph y equals e to the x. Menu. Go to your graph. Delete whatever graphs you have here. How will I graph e to the x? I'm going to go second function ln, and your calculator is going to, Brendan, when you do that second function ln, it's not going to show you the to the power of, but you know it's there. You don't have to add it yourself. For ours it does.
Where's ln?
I don't know. How do we just find the e? Shift right here. So now I know you weren't following along on the last one. Busted! Okay, so it's shift ln, shift ln, to the x. Now, before you can hit graph, but you know what? E, was that a number bigger than 1 or smaller than 1?
Bigger.
Bigger. So you know what? It's going to be one of these. It's going to be an exponential function. I guarantee that gets bigger. It goes through 0, 1. It has as its asymptote y equals 0. It has as its domain all reals. It has as its range everything greater than 0, but not touching. It looks like this. Yoink. Goes through it has the domain has a range, has no x-intercept, has a y-intercept of 0, 1, and it has as its asymptote, it gets closer and closer. It's an exponential function. It has to. So I'm not surprised, but it's nice that it fit the pattern. That's convenient. I think that I shall never see a number quite as nice as E. And again, it's kind of weird. E's a number. It is in math. Euler's number. And I wish if you took calculus, you would find why E is so nice. There's a wonderful calculus explanation. It turns out that the graph's height is also its slope at any location. But that doesn't mean anything to you guys right now. Sorry. Put your pencils down.